Okay, welcome back, guys. We are rounding out the term. This is the last section that I really want to go over. I might cover it in two lectures. I'm not sure. We'll see how far we get today. But this is changes of coordinates. And I'm going to start by trying to paint a little picture, give an idea. At this level, it should hopefully come out pretty simply. Let's say that we are measuring in one dimension. We'll call the variable x. And we draw these little tick marks every so often. We all know what those are supposed to represent. They're in this picture, they're supposed to be uniform steps of a certain amount. You could say, for instance, 1, 2, 3, 4, 5, etc. And they correspond to the idea of measuring a distance with some measuring object, like a ruler or your foot or whatever you might use. And the measuring object is this long. So here we have one of the object, 2, 3, 4, and 5. Now there's nothing significant about the number 5, and here is the conceptual leap that is really at the heart of all changes in coordinates. But a different coordinate system, U, and let's say that my measuring stick, and that gives me the U coordinates, is twice as big. So with this measuring stick, I could look at this same region in space. And I could come along and I got one tick mark here, two tick marks there. By the time I get there, I'm only at 2.5. I'm going to use letter D for domain for this orange region. The domain D can be thought of as representing some amount of space along a line. The coordinate system coming from X and the coordinate system coming from U are two distinct ways of measuring D. I'm going to try to integrate. I think a constant function should be enough. I'm going to imagine that I'm looking at this domain D in the um, well, let's do the x coordinates first. So here's my constant function. Maybe we'll put like a 2 there. If I integrate from 0 to 5, my constant function 2 times dx, I'll get this area here. Let me make this a little bit bigger. And you can think of it as coming from adding up the areas of all these rectangles. Now, when you understand what a Riemann sum is, you understand that you can read this expression here as saying, well, as x moves from 0 to 5, and I collect all the area coming from moving an x in the base and having a height coming from my function, I'm collecting all this height here along with this movement in my base. The total area I sweep out is whatever this integral comes out to be. It's going to be 10, of course. Now here's u. U would only move from 0 to 2.5. Is there a way to convert from u to x? X is equal to 2u. Let me write that up to the side more. So let's say that I moved from here to here. There is a delta x corresponding to that movement there. And according to this expression right here, if I move x by a certain amount, if my in the x coordinate system I move by a certain amount of numbers, and I look at what that corresponds to in u, the length is the same, of course, but the amount that I've changed in terms of the numbers ticks for u is only half as much. So let's say we're right here, and I want to do an integral in u. U goes from 0 to 2.5, and I integrate my function, the same function too. In this case, I'm only going to get a 5, which is not the same as 10. That's fine. In the u coordinate system, we're only going from 0 to 2.5. In the x coordinate system, we're going from 0 to 5. But here's the deal. One of these is the one you want, for whatever reason, for whatever measuring system you're in, or however you might think about it. One of them is the one you want. And so the question is, how do you get the one you want, the number you want, which in this case is 10? I made a mistake. This should be a du right here. Integrating in the wrong coordinate system. I want to integrate over here. I want to write out something like this. but I want the number to come out to be 10. Well, we go to one of these little rectangles over here where I try to set up my Riemann sum in U. And I think when I set up this Riemann sum, that rectangle is going to have a height of 2 and a length of du. I want it to have a length of dx or delta x. I really want to add up 2 times delta x. So instead of putting the function 2 times delta u, we set up a Riemann sum where we use the base length we would get in the x coordinate system. And in the end, this ends up giving us, I'll put it up here, one more factor of 2 right there. If x is equal to 2u, u is equal to um, then dx is equal to 2 du, and the integral from 0 to 5 of 2 dx is equal to the integral from 0 to 2.5, 2 times, well, dx is 2 du. What is that right there? That's just u substitution. When you do u substitution, you just have a relationship between x and u, and therefore a relationship between dx and du. And anywhere you see x's in your integral, you can switch them with u's as long as you do everything appropriately. And the final answer will be unchanged. Like in this case, it comes out to be 10. The original answer was also 10. We're allowed to switch all the variable names out without changing the answer, as long as we're careful, in particular, to keep track of that dx and du relationship. So you learned this when you first learned calculus, integral calculus. But look here. Hidden inside of all of that, that hidden inside that technique is this idea that x and u may both represent distinct coordinate systems on the same object, an interval, for instance, or in a two-dimensional object in a second when we go up. And the way you put coordinates on the object is up to you, as long as you keep track of how sizes change, basically, when you switch from one coordinate system to another. I'm going to say this without going too deep into it. Note, if you look at this expression, whoops, which is the kind of the core expression of U substitution coming from the chain rule. This is a similar expression to the following. I'll write it out the whole. So let's do integral. F of, let's do the following. Right? When we use polar coordinates, there's the integral part, which is the same up here. But look, just like here, we plug in a function of the new coordinate u. Here, the x coordinate is some function of r and theta. And well, now we're in two dimensions, so we need another function for y. Y is also some function of r and theta. So in one dimension, we plug in a function of u. The integral gets to be an integral in u now, and never we never forget this g prime term here in u substitution. And here, look, it's the same thing. I don't like how close that I is. There's a quantity. In this case, it's r. It's like that g prime of u. In this case, it was 2, as in to say we double the length when we change into the x space. For a general one-dimensional thing, it's g prime. And for polar coordinates, it's this variable r. So we want to build, I'll just say this right now, want general coordinates on R2. Right now, we only have rectangular coordinates and polar coordinates. And we want to use these one-dimensional chain rule use substitution ideas here to find a way to accurately do integrals for a general coordinate system on R2. So we've got to build this. I'm going to start by talking about transformations. So the general idea here is that x will be a function of two coordinates. In this case, we use u and v. It doesn't have to be polar coordinates, so we don't use r and theta. Y will also be a function of u and v. You can visualize this a number of ways. One of them is the following. So here's u and here's v. Here's x and here's y. One way of visualizing it is you're going to have some shape in x and y, and it's going to be hard for you to contend with. So I'm going to put maybe that same orange star here. Star. This side is what we want. But like in polar coordinates or like in a general use substitution setting, you're going to be looking over here and the coordinate system you have, so these X and Y rectangular coordinates, doesn't really work well with the shape you have. And you're somehow in your back pocket, there's some geometric knowledge you have. You're going to have some choices of G and H there that put very nice coordinate lines. Think like polar coordinates, how polar coordinates look different than rectangular ones. And the coordinates you get are going to look like they work really well with the shape you've got. What that means is there's going to be a nice shape in U and V, something like this. And we're going to take that shape and map it onto this weird shape using two functions, G and H. And what that's going to mean is when you look in X and Y and you see these weird green coordinates on my new shape, you're not going to have to think about it that way. You're going to be able to think about it as though you're over here in U and V and you've got these beautiful, nice rectangular coordinates where you can set up integrals very easily. The math is very easy. But to be fair and for this to work, you will have to acknowledge the size of that little rectangle there is not necessarily the size of the corresponding shape over here. And the change in that volume or area in this case from here to here is regulated by this thing we call the Jacobian. It's that factor of R. So this is like R or like G prime of U in the U substitution case. It's something meant to measure distortion of area. And you need it if you want to pretend you're in this nice space over here, but you really care about what's over here. The Jacobian is kind of the price you pay to 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 have that nice setting or to think in terms of that nice setting. Okay, so in general, a transformation T, which gives X and Y coordinates from U and V coordinates is two functions, G and G of U and V and H of U and V. And we need something. The pair must be 1, 2, 1. What that means is, so I'll say i.e., no two distinct points U1, V1, and U2, V2 map to the same pair X comma Y, or the same point X comma Y. So you're not allowed to fold your rectangle over on itself and double down on points. Just jump right in with an example so we can actually have something uh, that we're familiar with and that we can think about. So the first one is really easy. Transformation uh, coming from the polar coordinates, r cosine theta, r sine theta. Let's just think about it in these two distinct spaces. 0 to 1 is 0 to power 2. We'll take r from 0 to 1 and theta from 0 to pi over 2. And we're just going to sketch a little bit. So when you see r going from 0 to 1 and theta going from 0 to pi over 2, you see something like this. They're constants, 0 to 1, 0 to pi over 2. It's a rectangle. What do you mean it's a rectangle? It's supposed to be like radial lines and angular lines. But that's only in X and Y coordinates. If I put X and Y rectangular coordinates on the plane and I look at the transformation X equals R cos theta and Y equals R sine theta, well, if you fix a theta and you move along a Y line like this, so this is maybe pi over 4, what will X and Y do? They are going to move along this 45-degree angle. And then you go up to a different line, a different fixed theta, and you look at this transformation and X and Y will move along a different ray. And so what that means is over here, I don't want to draw so many lines, it's really hard, but our rectangle and R and theta got distorted. Let me just ask you very quickly and ask yourself this question. Is T 1 to 1? I don't want to write out a mathematical proof that it is, but I want you to observe that it is. If you pick 2 points, let's do a green point and maybe a purple point. Any 2 points in the R and theta space, is it possible under this map? Well, actually, there's a little bit of a trick question in here, that those 2 points get mapped to the same place over here. Hopefully you can see they won't. Maybe the purple point gets mapped there and the green point gets mapped here. There's a little bit of an issue, and I'll just say it and kind of be done with it. When R equals 0, there is actually a huge amount of not one-to-oneness. That whole line of points right there, doesn't matter the choice of angle, R is 0. They all get mapped to the origin. I'm gonna actually just circle this and say, we ignore this detail when we teach polar coordinates. We ignore this detail because we all kind of understand on some level that one point isn't what we're interested in. We're doing integrals over regions away from this one bad point. It's too subtle of a detail to acknowledge. when you first teach polar coordinates, kind of gloss it over and push on. But we all know this. We all have some sense of an understanding that when r equals 0, all of these different points in theta, they're all mapped to the origin. So strictly speaking, it's not one-to-one, but I'm going to say yes away from r equals 0. So for the examples in this section, we're typically going to try to look at things that really are one-to-one. But we'll admit for polar coordinates, because it's such a special coordinate system, so important, so useful, that it can have this one little problem, and we'll pretend not to notice. Okay, so that's one example of a one-to-one map, so a transformation. We've seen it a bunch of times. We're just observing here that there are two ways of thinking about r and theta. They could be given their own Euclidean rectangular coordinate system, in which 0 to 1 and 0 to pi over 2 give us a rectangle, or we can think of them through the transformation to x and y, in which they give us this polar rectangle, this quarter circle. And both could be reasonable ways of thinking about things. We all kind of understand the one on the right is the one we care about. But you never know. Maybe in a different setting you wouldn't care. Yeah, I've got one more example here of a basic transformation. Where is it? Yeah, and this one, this is a new one. We haven't ever seen this one before. And the idea here is there's really nothing special about it. There's so many coordinate systems, and when you kind of develop the skill, the freedom is yours to put any coordinate system you want on a space. And so it's good to see a few silly ones, or not silly is maybe the wrong word, but not impressive, not a that's what I'm looking for. Oh, I can't remember right now, but u squared minus v squared and uv. I mean, this was actually maybe a little bit more important than I just said, but I'm gonna ignore that. Okay, here they give us a transformation. Unremarkable. That's the word I wanted. All right, in this case, G is u squared minus v squared, and H is UV. So just on its face, I'm going to ignore the fact that this is one to one. Don't worry about that. But on its face, what do we have? We have X expressed as a function of U and V, Y expressed as a function of U and V. Okay, then this is a transformation. Ignoring the one-to-one detail, it is one-to-one. And they give us a region in U and V. Let's see here. What was it? 0, 0, 0, 1, 1, 1. So the question that they're asking us here is the following. If I start in U and V, and I draw a triangle, so here's U, here's V, here's wait, hold on. Let me make sure I do the one that they want. 0, 1. So here's 0, 1, here's 1, 1. And then here's the origin down here. We get a triangle in U and V. What does this triangle look like if we transform over to x and y? The transformation t takes us from u and v over to x and y, but it might do it in a weird way. I'm gonna just start by doing the corners because those tend to be really easy. Where does 0, 0 map in this case? Hopefully you can tell it goes to 0, 0. 0 squared minus 0 squared is 0. 0 times 0 is 0. So that's the same point. Actually, you know what I should have done is different colors. Yeah, let's do that. That's the same point. How about this corner right here where u is 0, but v is 1. Well, 0 squared minus 1 squared is negative 1. 0 times 1 is 0, so x will be negative 1. Y will be 0. That green point right there got mapped to that green point right there. Give me one more. Let's do 1, 1. Whoops, hey, give me my new color. 1, 1. Now, where does that point go? Well, 1 squared minus 1 squared is 0, so x will be 0. But 1 times 1 is 1. That's 1, 1 right there. I should have labeled these, at least the two non-origin ones. You guys see that? Those points got mapped to new points over here. It kind of looks like a triangle. Just because those points got mapped like that does not mean that this shape is going to be a triangle. We now have to ask, well, what about the edges? Let's try actually, that's going to be a harder edge. Let's try the easier one first. Let's try this one right here. Well, if I move from 0, 0 to 0, 1, I'm only ever changing V, right? So if I look at that edge there, X will be equal to 0 squared minus V squared, and Y will be equal to 0. So that actually does move. So that's the same as a negative V squared comma 0. V squared is going from, well, V goes from 0 to 1. V squared goes from 0 to 1. So I do see this edge here. Let's try another one. Let's try this guy right. No, no, I already did blue. Let's try red. Will red help? Along that red edge there, V is 1. So X is equal to U squared minus 1. And Y is equal to U times V is just U. Now, what does that look like? And here, of course, U is going from 0 to 1. What does this look like right here? Hopefully, everybody can recognize that as a parametric curve, X and Y as functions of U going from 0 to 1. Well, if Y goes from 0 to 1, because U goes from 0 to 1, and X goes to U squared minus 1, what does that look like? I'm gonna write it this way. If x equals y squared minus 1, we're seeing a parabola. Actually, that was pretty good, I guess. That line right there is why is it not letting me grab it? Come on. Okay, I don't know why it's not letting me, but it didn't get mapped to a straight line. Our coordinate system is a little wonky. Let's get that last edge out of the way so we can see the external shape, and then maybe we'll jump into the interior. Yellow, purple. I guess purple is good. This edge here. How am I going to do that edge? On that edge, U equals V. And therefore, X equals 0, U squared minus V squared. And Y equals, you could say U squared or V squared, it doesn't matter, going from 0 to 1. And so we do see this edge here. Now, there's one more thing I'll try to highlight, or maybe two more things. These light blue lines here are all like the red line. They're parabolas, but they're slightly different parabolas. Oops. And so this gives us coordinate lines like this. Not so proud of how I drew that, but I'll take it. Um, and then there's one more, which is, I guess I'll just try yellow, these vertical lines. For those vertical lines, U is fixed. Let's try those. The vertical lines, U is fixed. You'll see X equals some constant minus V squared. And Y will also equal some constant times V. What do those look like? Let's see, what's the easiest way to see one of these? Yeah, just for the sake of visualization, plug in one first. So just imagine 1 minus V squared and V. 1 minus V squared looks like this. Or one, well, if Y equals V, then it looks like this. Now that's not on our shape, but if I take U initial to be like 1 3/4 or 1/2 or 1/4, I get smaller, or parabola is more like this. And I see lines like this. These yellow lines here are subsets of graphs of parabolas. These blue lines are also subsets of graphs of parabolas. A nice, weird looking, interesting coordinate system. The shapes locally are not little rectangles, but over here they are. So something like that little rectangle there gets deformed to this weird looking, almost it's like a parabolic parallelogram. Let me freeze here. I think for this week, because there's not much to learn, we can go a little slower. And this is already a lot to digest here. So let me just zoom out and try to recap what we just did today. And then I think there'll be one more lecture rounding this all out. All we're talking about today is that you can put different coordinate systems on the same shape in one dimension. You can also put different coordinate systems on the same shape in two dimensions. Oh, of course, the picture gets much more interesting. And I guess you want to practice now just visualizations and drawings. So there's no homework due this week, which means you're free to go to section 5.7 and do whatever problems you want. But any problems that ask you to sketch or visualize things would be great for today. And then tomorrow I'll give one more lecture on how to set up integrals in these systems, and we'll call that a wrap for the term. Please email me if you have any questions, and thanks again, guys.